And neutral means it's around what number?
7.
7. So if I have a neutral state indicator, and then I've got sodium hydroxide and hydrochloric acid, what kind of reaction do you think I have going on? Yes, chemical. What's happening here? What's involved that's causing the color change? If we have an indicator, which indicates
pH.
Okay, exactly. So we have a pH change going on, right? We start out with sodium hydroxide. Anytime you see an "ide," it usually means it's a basic substance, which means it's a base. And that means it has a pH of about around what area? Is it higher or lower than 7?
Higher.
Higher. Yes, bases have higher pH. You guys are the first class to get that one right.
Everybody says lower.
That means that acids have a what pH? Lower pH. So if I go from a high pH and I pour it into an indicator solution, and the indicator solution turns a color that's telling you that it has a base substance in it, and then I take that indicator solution with the pink and I pour it into an acidic solution. So I'm mixing an acid and a base. What's going to happen to the pH?
It will neutralize.
Yes, and when it's neutralized, it's clear, right? Looks like water. So in this case, it is in fact a chemical change.
More than one chemical change.
More than one chemical. It's changing pH several times. pH change, it means it has to do with the removal of a hydrogen. You guys don't really need to know that, but okay. Number 2. Thoughts. Go ahead.
Me?
Yep.
I said a physical.
Why do you think physical?
Because you poured something onto it,
Mhm.
which and it wouldn't have caught fire green if you wouldn't have poured that on.
Okay.
Chemical because it changed color.
It did change color. The chemical change is not really with the color.
There's really, I think it was physical because there was really no change at all except when you poured the liquid on, that's what created the flame.
Okay, let me tell you what liquid I poured on there. I poured isopropyl alcohol, or rubbing alcohol. It's extremely flammable. What happens when you have a fire? You have a fire, a flame. What does that tell you? Now,
There's heat.
there's heat, there's energy being released. If there's energy being released, is that a chemical or a physical change?
Chemical.
Chemical change. So in fact, this one is a chemical change. Now, the question is, can anyone figure out why adding copper sulfate, this blue crystal, which by the way does not burn, you're not seeing it burn, it's still there, I haven't added any extra, makes it green. Because isopropyl alcohol,
Ooh, I'm glad you had the lid on that.
yes, does not make a green flame.
Because blue and then like the fire's kind of yellow.
Okay, you think the colors are combining.
That's a good
There
thought.
might be a little bit of that involved, but that's not the main reason. It has to do with electron shells, which I know you guys have talked about a little bit.
Yesterday, remember we talked about cesium and how each electron has its own shell? Remember orbital shell? We talked about that
It has
yesterday.
to do with energy levels. So what's happening here is when you light a fire, there's energy being released, right? That's what fire is. It's energy, heat energy. So
Is it matter if it's energy?
No.
No.
Okay, good. Whew.
So when I add energy to this this copper sulfate, you're exciting the electrons in the copper sulfate, in the outer shell of the copper sulfate. Remember, it was the cesium.
Mm-hmm.
Cesium had six electron shells. The outer shell is the one where the electrons are reactive. They get the brunt of anything that happens to that cesium. And that's what happens here in the copper sulfate. The outer electrons get the heat, they get the energy, and they get excited. And they start bouncing around, they start spinning around, they get real high energy. And they do that for a little while, and then they slow down. And when they slow down, all that energy has to go somewhere. It doesn't just disappear. So when they slow down, that energy is released as a light photon of light. And so when they release that light photon, it actually makes a green glow. So what you got is a whole bunch of electrons getting excited, slowing down, getting excited, slowing down. And so they're releasing green glow, and you end up with a green flame. That one is in fact chemical change simply because a fire was present. Now, this one's been a little bit of debate, had a little debate in the last couple of hours. We have crystal ball, using frozen carbon dioxide. Thoughts?
I think it's a physical because the carbon dioxide just melted.
Carbon dioxide just melted. Okay.
I think that it's a chemical because something new was created.
What was created that was new?
A gas.
Okay. Gas was present. Yes, gas was made, and basically all I did was put bubble soap around it to make a cool crystal ball effect. So if I'm putting solid carbon dioxide, which is about a negative 109 degrees Fahrenheit, into warm water, what's happening to that solid carbon dioxide?
It is melting and creating the gas.
But doesn't it typically go from a solid to a liquid first?
Where's our liquid carbon dioxide?
What if it's just going so, like, it's so cold and it's so warm that it skips the whole solid?
Ding, 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 ding.
Excellent,
Gold
Ethan.
star for the day.
I get a gold star.
Not really.
You need to press the-
Like I said, carbon dioxide, when it's in a solid form, is about negative 109 degrees Fahrenheit. That means when you put it in room temperature, the difference in temperature is so great, it goes straight from a solid to a gas. It pretty much skips the liquid form. This is a process known as sublimation. Ooh, fancy.
Sublime.
There's your new term.
New word. It's like evaporation, which is from a liquid to a gas, except this is from a solid to a gas. And that's what happens when you place, actually carbon dioxide solid will do that at room temperature. It's actually doing that right now in that container.
It'll even do it in your freezer.
Yes, it will.
You cannot freeze carbon dioxide, frozen carbon dioxide. You can't take it home and put it in your freezer and save it. You'll come back in several hours and it'll be all gone.
They have to keep it extremely cold. And
Your freezer's not cold enough.
They use it a lot for transporting frozen items from in trucks and things, but it does break down pretty fast. And that's the same thing with Little Smoky here. The carbon dioxide is going straight from a solid to a gas. So if we're just changing state of matter, is that a chemical or a physical change? Is a physical change. Question.
Then where do they store the dry
I assume they probably have freezers that can get cold enough to hold it for long periods of time. I assume. I'm not entirely sure the process of how they even make the dry ice, how they get it. I didn't really research that a whole lot.
Dry ice. Or cool, buy dry ice.
Well, that sounds great, but I don't know how it would work. Okay, dollar bill. And yes, it did work exactly as I wanted it to. So, physical or chemical change?
Physical, 'cause nothing new is produced.
Technically, nothing happened to the dollar bill, but the demonstration itself, was it a chemical or physical change?
Chemical, because there was a fire present.
Yes, Lexi.
There was a flame present, and a flame indicates that a chemical reaction is taking place. Even though the dollar bill was undamaged, there was in fact a flame.
Except in first hour when you
Except
caught
in
it on
first hour
fire.
when the table was on fire.
Table's on fire?
A little bit.
Fine.
That's, no.
That was the
That's-
old.
No,
that's
that's
the old
old.
burn. Now, I got a question for you. Why did the dollar bill not burn?
Because the chemicals that were layered on the outside were the ones that caught on fire, and the bill was underneath all those chemicals where it didn't affect it at all.
That's pretty much right. I had isopropyl alcohol, like we've used before, which is extremely flammable, mixed with a mixture of water and salt. The salt was added to add more color to the
I'm
flame.
gonna talk to you about it
But
later. Okay.
the water was added to protect the dollar bill from burning. And that was the problem in first hour. I didn't have a very good combination of water and alcohol, and so the dollar bill actually caught on fire. In this case, however, if the water molecules simply don't get hot enough, they're on the dollar bill and they don't get hot enough to burn, and the isopropyl alcohol will burn so quickly it doesn't have time to touch the dollar bill. But it is a chemical change simply because a flame was present. Last but not least, elephant toothpaste, chemical or physical?
Chemical because the molecules started to expand and made it foam.
Chemical because there was bubbles.
There were bubbles being made, but that doesn't always, I mean, it's a sign that it could be a chemical change, not always true.
Physical because something new was produced.
If it's a new substance, it's going to be a chemical change.
Chemical because it started rising.
Well, we've got that over here too, with the bubbles making that rise, and that was physical. So
I think that it was producing a gas which made it bubble,
okay,
which is
a chemical.
change.
Yes, it is a chemical change. So the only one that was a physical would be these two here, this little smoky and the crystal ball. Now, in this elephant toothpaste demonstration, I used hydrogen peroxide, which you probably have in your house. Where would you find it in your house? Just say it. Yeah, like medicine cabinet, bathroom. And what would you use it for?
Like if you have burns or something, you can put it on your burn.
And what happens when you put hydrogen peroxide on your arm? It does burn. Have you ever looked at it though?
Like bubbles.
It bubbles.
What does it turn? What color does your skin turn?
Purple.
Kind of a white, actually.
So I have all these chemicals here. What's the difference between this bottle and the other ones?
The hydrogen peroxide, it has to be in a dark container because if sunlight gets to it, it'll evaporate.
That's exactly right.
Do you remember the other chemical we used in class that was in a brown bottle? That I showed you? And we talked about why it was in a brown bottle. Iodine.
Hydrogen peroxide is actually a very unstable chemical. It breaks down really fast, and especially if you expose it to heat or light. That's why you should really keep it in a kind of cool area, especially dark area. They keep it in these brown bottles to kind of keep the light out, and they will actually break down over time. So if you have some hydrogen peroxide at your house and you haven't opened it in quite a while, it probably has some pressure underneath the bottle from where the chemical is broken down and the gas is released.
And when it says the expiration date on it, it means that it's expired. And when it's expired, it's no longer
I would-
hydrogen.
you should not use it.
Yeah,
It's probably mostly water at that point.
yeah.
Um,
Show them what hydrogen peroxide looks like chemically.
Yes. They actually have special bottles that they make for higher concentrations of hydrogen peroxide, which we were going to use on this, but we didn't get it in time. And the bottles actually expand. They'll grow upward while they've got little folds in it, so it'll grow upward while the hydrogen peroxide breaks down. Let's see. Hydrogen peroxide is this is the reaction that's occurring. Okay, so what can you tell me from this formula?
It has H2O in it.
It does have H2O, and it's on the other side of the arrow. In chemistry, when they write out arrows, that means a reaction has taken place. So this would be the original ingredients, and then this would be the final product.
It's using the second isotope of hydrogen.
They're saying
And
that.
keep thinking that. This in chemistry is actually a symbol of balancing the equation. If you ever take a chemistry class, which you probably will, you have to balance your chemical equation, and basically it's doing the math. So it's saying that 2 molecules of hydrogen peroxide. It's not actually the isotope.
That would be 2H.
A lot of people have been thinking that, but that's not the isotope.
But I'm really proud of you guys for remembering. I'm so happy that you're remembering the isotope.
So this 2 here means that you have 2 molecules of hydrogen peroxide. What does that 2 mean? 2 hydrogen and
2 oxygen.
So what's the difference between hydrogen peroxide and just plain water?
It's because
Molecules.
Yeah. So just that. Go ahead, Aaron. Sorry.
so that one little difference actually makes that it seems small, that it only has 1 extra hydrogen. That shouldn't be a big difference, but it makes an enormous difference between hydrogen peroxide and water. Water is a very stable molecule. It can absorb a lot of heat. Hydrogen peroxide is very unstable, and you should never heat it. Let's see. What do you think these little symbols, the L, the G, and the AQ stand for?
liquid and gas.
Okay. Anyone thoughts on the AQ?
Aqua.
Close.
Close.
Oh, yeah.
It's aqueous.